All right, so now we're going to look at another example of a manifold of probability distributions, and in particular, let's look at the space of discrete distributions. Okay, so let's say that you have some discrete random variable. So let x be a discrete random variable. Taking values on space big X, which is just a set of possible outcomes, let's say 0, 1, all the way up to n. Okay? So a probability distribution on this space X, let's call that P of X, right, is specified by sort of assigning the probabilities of each of these outcomes, right? So n plus 1 of these probabilities, right? Which I'm going to denote by P sub I. So P sub I is the probability that X is equal to I, right? And then I goes from 0 all the way up to n, right? So I is enumerating, it's like this set X of possible outcomes. So, so with that in mind, it's like then you can think of P of X as being some sort of vector. So P of X, right, is represented by a probability vector. So let's write this as P, and this is just P0, P1, all the way up to Pn, right? So this is this is in Rn plus 1, if you will. Okay, but it's not all of Rn plus 1 because there are some constraints. It's like on, you know, these probabilities. Okay, in particular. Okay, so we have a restriction that the sum of the probabilities is 1. Okay, so there's some sort of normalization condition, and that Pi is greater than or equal to 0. Okay. So the set of all of these probability distributions forms an n-dimensional manifold. Okay, and if you're not clear, it's like why it is that it's an n-dimensional manifold as opposed to an n plus 1 dimensional manifold. This constraint, it's like the normalization condition, means that all you really need is all but one of these coordinates, right? So if you know, for example, P1 to Pn, then by the normalization condition, you know what P0 will be. So if you will, it's like, you know, this space of discrete distributions can be, you know, you can have a chart on this, which just involves all but one of the components, if you will. It's like of this n plus 1 dimensional probability vector, okay, because of this constraint, if you will. Okay. So let me try to make that a bit more precise. So, well, we can have a coordinate system given by, for example, just the P1 to Pn components, right, of this, right? And this is because P0 is not free because of the normalization condition. So P0 is just going to be 1 minus the sum from I equals 1 to n of Pi, right? So the point which we talked about earlier is that given P1 to Pn, you can infer what P0 is through the normalization condition, right? Okay, so this is 1 minus the sum of the coordinates, it's like which we have here. Okay, all right, so that all makes sense. And so that has n degrees of freedom, right? So again, it's like it's an n-dimensional manifold, which is embedded in an n plus 1 dimensional space. Okay? All right. So what does this manifold look like? Okay, so the manifold in question is an n-simplex called a probability simplex, which is denoted by Sn. Okay, so let's try to think about what some examples of this are. So when n is equal to 2, S2 is the interior of a triangle. When n equals to 3, it is the interior of a simplex, like a pyramid, if you will. Okay, so let me sort of just draw the S2 case. Okay, so this is the triangle for n equals to 2, right? And then right, and anyway, so that's an example. And you can introduce some random variables, okay? And then what we're going to do basically is that we're going to introduce a different sort of coordinate system, if you will. It's like for these space of discrete distributions. So let's consider the following n plus 1 random variables. delta I of x. I goes from 0 to n, and delta I of x is equal to 1 if x is equal to I, and 0 if x is not equal to I. Okay, so this is basically just the Kronecker delta function, all right? Then you can write, with that, it's like you can write down any probability distribution. It's like a appropriate linear combination of these random variables, okay? Then the probability distribution of x is denoted by the following. So P of x, it's like given some coordinate on that space, right, is equal to the sum of Ci delta I x, I equals 1 to n, right, plus 1 minus the sum of Ci, I equals to 1 to n, times delta 0 of x. Okay, so given a point, it's like in, with respect to this coordinate chart, which we talked about, right, this is the associated probability distribution. Okay, so another possible coordinate chart is given by the following. Okay, so theta I equals to log pi divided by p0. I goes from 1 to n is also useful. So one thing it's like to notice about this particular coordinate chart, right, is that clearly that has the potential to break down if p0 is 0, right? And that's what sometimes happens. It's like when you have these coordinate charts, is that the coordinate chart doesn't cover the whole manifold, basically, right? And this would be an example of where it doesn't cover the whole manifold, because it's like this coordinate system makes sense when p0 is not 0. And we don't know ahead of time that p0 is not going to be 0, but we do know that one of the pi's for I going from 0 to n will be non-zero. So there will always be some coordinate chart. It's like of this kind of form, but with a different denominator in this quotient, right, for which you can write down a local coordinate around that. So yeah, and so that's the nature, it's like, of working with manifolds. It's like in atlases, is that there are coordinate singularities, all right, at the boundary, it's like of the domain of definition or coordinate chart oftentimes, which prevents a single coordinate chart from covering the entire manifold. And that's the reason why you oftentimes have to resort to multiple charts which overlap in order to cover the whole manifold. Okay, so this is an example of a coordinate chart which exhibits a coordinate singularity at some of the points, it's like in the manifold, which forces you to choose a different coordinate chart if you want to parameterize the area around that point. Okay. All right. So and so we looked at this space of Gaussian distributions, and we look at this space of discrete distributions, and these are examples of what are called regular statistical models. Okay, so the remark is that space of Gaussian distributions and the space of discrete distributions are examples regular statistical models. So a statistical model right, is a family of probability distributions and when it satisfies certain regularity properties, refer to it as a regular statistical model. Okay, and so information geometry then arises from the study of invariant geometric structures associated with regular statistical models. Okay, all right. So, these are just again some examples of regular statistical models. It's again, they're possibly the simplest examples you can think of, and so just keep this at the back of your mind as we start introducing some of these additional differential geometric structures, which are going to build on top of this. So let me just stop here for now.